Hello students. നമ്മൾ ഓൾറെഡി ചെയ്യുന്നതിനകത്ത് വരുന്ന ഒരു പ്രോബ്ലത്തിൻ്റെ കണ്ടിന്യൂഷനാണ്, ഒരു സിമിലർ പ്രോബ്ലമാണ് ഞാൻ ചെയ്യുന്നത് ഇവിടെ. ഇപ്പോൾ ക്വസ്റ്റ്യൻ ഇതാണ്. A simple evaporative air refrigeration system is used for an aeroplane to take 20 tons of refrigeration load. The ambient conditions are 20 degree and 0.9 bar respectively. The ambient air is rammed isentropically to a pressure of 1 bar. The air leaving the main compressor at a pressure of 3.5 bar is first cooled in the heat exchanger having effectiveness of 0.6 and then in the evaporator where its temperature is reduced by 5 degrees Celsius. The air from the evaporator is passed through the cooling turbine and then it is supplied to the cabin, which is to be maintained at a temperature of 25 degrees Celsius and a pressure of 1.05 bar. And the internal efficiency of the compressor is 80% and for the cooling turbine is 75%. If so, determine mass of air blood of the main compressor, the power required for the refrigerating system and COP of the refrigerating system. So here the air is get rammed and the refrigerant air, the air which is coming from the compressor is going into the evaporator as well as the heat exchanger. Okay, so we have to draw a TS diagram based on the things given or how the aircraft refrigeration system is produced. Okay, so given things are the tons of refrigeration is 20, initial temperature is 20 degrees Celsius and initial pressure, ambient pressure is 0.9 bar, the ramped pressure is 1 bar, the final pressure means the compressed pressure is 3.5 bar, then efficiency of effectiveness of the heat exchanger is 0.6, then cabin temperature is 25 degrees Celsius we have to maintain, as well as the pressure is 1.5 bar, compressor efficiency 80% and turbine efficiency is 75%. Okay, so this is the TS diagram where the air from the ambient air is being taken into the jet where it is being rammed isentropically. So it is given as isentropic compression has been taken place in the ramming process, from where it is compressed isentropically in the main compressor, but the efficiency of that compressor is given so that there is a frictional losses. So it is actually an irreversible process, so it falls into 3 dash. So and it is a final pressure remains the same, and from where it is the compressed air is taken into the heat exchanger where it is being cooled and the heat exchanger is having a effectiveness, and then into the heat exchanger where the evaporator where it is being further reduced the temperature from 4 to 5, it is being expanded in the cooling turbine and the turbine efficiency is also given, so it is an irreversible process. It is falls to 5 where irreversibilities are associated, and it is into the cooling cabin. So all the temperature associated with the process are given, and for the ramming process, for that I have to erase everything. So isentropic ramming process 1 to 2, it is a ramming condition. We have to find out all the unknown temperature values here. Okay, so we are given some initial conditions, temperature, pressure, and missing temperature, pressure conditions we have to be find out if they are missing. T2 by T1 is equal to P2 by P1 the whole raised to gamma minus 1 by gamma. This is the temperature pressure relation for an isentropic process. So from this equation I can find out the temperature T2, means the temperature after ramming is 301.8 Kelvin. The gamma value for air is 1.4. Then we have to find out the isentropic efficiency 2 to 3. This happening in the main compressor. Again T3 by T2 is equal to P3 by P2, same pressure temperature relation. From the relation we can find out the unknown temperature T3, so that is 431.6 Kelvin. Okay, then I have to find out the another temperature which falls on that irreversibilities, that is T3 dash. So for getting that temperature value I have to use the efficiency of the compressor. So isentropic efficiency, so an efficiency of the compressor is equal to isentropic increase in temperature divided by actual increase in temperature. So we know that I just mentioned a shortcut for getting this equation in our previous class. T3 minus T2, that is the isentropic increase in temperature divided by actual increase in temperature, that is T3 dash minus T2. Okay, so efficiency of the compressor is given as 80%, and from the unknown temperature, that is T3 dash, is obtained as 464 Kelvin. Then I can find out that now I've got the temperature T2, T3 dash. I can find out T4 by using the effectiveness of the heat exchanger. It is 0.6, that is T3 dash minus T4 divided by T3 dash minus T2 dash. What is the effectiveness? But this equation is actually studied in the sections where the exchanger comes. And here T2 dash is equal to T2 because they told us to take that process as isentropic. So from that T4 is equal to 93.7 degrees Celsius, means that the compressed air temperature is reduced to this much of 93.7 degrees Celsius because of that heat exchanger. Okay, since the temperature of the air in the evaporator is reduced by 5 degrees Celsius, therefore the temperature of leaving the evaporator and entering the cooling turbine, that is T4 dash, means that evaporator pass the temperature is reduced by 5 degrees Celsius. Now means that T4 5 degrees Celsius T4 dash temperature. So T4 dash is equal to T4 minus T5, so that is 88.7 degrees Celsius, that is 361.7 Kelvin. Now we have the isentropic expansion process 4 dash 5. So T4 dash by T5 is equal to the relation P3 by P6. We know that pressure, all the points are the same. By using that relation I can find out the T5 value is set to 56.5 Kelvin. Now I need to find out the T5 dash value. For that I have to use that efficiency of the turbine. Okay, so efficiency of the cooling turbine is equal to actual increase in temperature divided by isentropic increase in temperature. So actual increase in temperature is equal to T4 minus T5 dash divided by isentropic increase in temperature is equal to T4 dash minus T5. So from that equation the missing value is T5 dash. I can find out that temperature value as 282.8 Kelvin. So when all the missing values are being obtained, I can go for the parameters what they asked. They are asked to find out the mass of air blood of the main compressor, so that is equal to MA, that is equal to the ton of refrigeration is Q, 210 Q divided by Cp into T6 minus T5 dash. This is the quantity of temperature is being taken away in the cabin. So the mass of air required for this tonnage of refrigeration is 276 kilogram per minute. So this is the mass flow rate of air required for getting the 20 tonnage of refrigeration for the reduction of temperature from 298 to 282.8. This is the temperature difference that we obtained because of this mass of this total quantity of mass of air. So power required for the refrigeration is equal to the power required for the refrigeration system is equal to power is equal to MACP into T3 minus T2 dash, because this is the only external work that we have to provide for the main compressor. So this is the terms comes in the main compressor part, because of the ramming process happens naturally, so we need not to take that value also here. So all the values are here, so I'm substituting all the values here, and I obtained the value as 746 kilowatt. Then we can find out that COP of the refrigeration system is equal to 210 kilo into ton of refrigeration divided by whatever the power required. So this the entire thing is comes in kilojoule per minute, so I have to convert into kilojoule per second. So for that I use that 60 value here. I'm converting this kilojoule per minute into kilojoule per second, and the power is obtained as kilojoule per second. So the efficiency, the COP of the system is obtained as 0.094. Okay, thank you.